Hi guys! So today's lecture is going to be on sorting algorithms. Let's go ahead and dive into the lecture slides. So sorting is the process of converting a list of elements into ascending or descending order. For example, given a list of numbers in no particular order, 17, 3, 44, 6, and 10, the list after sorting, or in other words, after applying a sorting algorithm, might be 3, 6, 10, 17, and 44. Now, of course, this would be sorting in ascending order, right? Notice how starting from the left, you have the smallest value number, and after that, each number is the next largest number. Now, numbers are not the only thing that you can sort. You can sort anything, really. And that's why we introduced earlier in the semester the comparable interface that gives us that compare to method. That allows us to now compare anything and determine if what you're comparing is larger or less than something else. And in using that, you could, in conjunction with sorting algorithms, you can now sort just about anything. So in this lecture series, I'm going to be covering multiple different sorting algorithms that all basically do the same thing. The difference between them oftentimes is how efficient they are and how easy they are to implement. You'll find that some of the less efficient ones are often more easy to implement for us because it's easier for us as human beings to understand what's going on in that sorting algorithm. So the first sorting algorithm that we're going to cover is selection sort. Selection sort is a sorting algorithm that treats the input as two parts, a sorted part and an unsorted part. Where the input is an array of unsorted elements. In the examples that we go through, there'll be an array of unsorted numbers. And so what it's going to do is take that array of unsorted numbers and split it into two parts, a sorted part and an unsorted part. And then it's going to repeatedly select the proper next value to move from the unsorted part of the array to the end of the sorted part of the array. And so what is the next value? Well, if we're sorting in ascending order, the next value would be the smallest valued item or element in that unsorted part. So let's go ahead and look at an example of this to better visualize selection sort. We're going to use zybooks for this. So here we have our, in this case, it is sorted. So we'll start here. Here we go. So here's our unsorted array of numbers. You can see that, clearly they're out of order. Notice any white box is considered an unsorted portion of the array, and any grayed box is the sorted portion. So right now, nothing is sorted. You'll see below it the selection sort code, and just at a brief glance, what you'll notice is a for loop, and inside or nested inside this for loop is a second for loop. And then what you'll notice below that nested for loop is this section of code right here, which is doing some sort of swapping. So yeah, let's read the comment down here. Selection sort treats the input as two parts, a sorted and unsorted part. The variables I and j keep track of the two parts. So we'll notice I starts at 0, which I guess in this case is going to be an index, right? So currently I is referencing index 0, which has a value of 7. And then j starts at whatever I is at plus 1. So j starts at, in this case, 0 plus 1, which is 1, which has a value of 9. And we'll see here in a second of how it's going to keep track of how those two variables are going to keep track of these sorted and unsorted portions of the array. So if we start, what ends up happening is this inner for loop, what it's doing is it's looping through using a linear search, looking for the smallest item in the unsorted portion of the array. And so you can see what they're doing here is they're incrementing the j index and comparing every item that they find, or element that they find, against whatever is currently the smallest element. How do they keep track of what the smallest element is? Well, here they have this index smallest variable. And this index smallest variable is going to be the index at which the smallest value resides. In this case, they've looped through every single element in the array, and they found 3 to be the smallest valued item. And therefore, index smallest is at 3. And you can see the comparisons here. 7 originally started as the smallest element item. They compared 7 to 9, and 7 was indeed still the smallest. But then they compared 7 to 3, and 3 is less than 7, therefore 3 became the smallest. And so instead of continuously comparing the 7, now they compare the 3 against the remaining elements. 3 is indeed less than 18, and 3 is indeed less than 8, and now we've searched or compared against all of the different elements in the unsorted portion of the array, leaving us with 3 as the smallest. And so now what do we do that we have found the smallest element in the array? And the answer is that's what the swapping section of code is for. The swapping section is going to swap the value at whatever index smallest is with whatever the value at index 1. So we'll go ahead and play this portion. Elements at I and index smallest are swapped. So that's the 3 and the 7. And now what do? We repeat the process. In this case, the 3 is now considered in the sorted portion of the array. We no longer need to check that portion, so what we're going to do is increment the value of I by 1, and now I to j contains the unsorted portion of the array. And the process will repeat. So there you are, there you have it. The 3 is in the sorted portion, everything else is in the unsorted. I resets to index 1, j resets to be I plus 1, which is 2. And now the searching for the next smallest element begins. So 7 was less than 9, 7 is less than 18, and 7 is less than 8. Therefore 7 is the smallest element, and it gets swapped with whatever was at I, which happened to be the 9. And now 3 and 7 make up the sorted portion of the array. And the process once again repeats. So we reset the I and j. We continue to find the smallest element, which happens to be the 8. The 8 swapped with whatever was at I, which happens to be the 9. 8 is now in the sorted portion of the array. We update the I and j again, and then we swap the 9 and the 18. And 18 is the last element, and so the sort ends. And here we have our sorted array, 3, 7, 8, 9, and 18. So of course in ascending order. So that's selection sort. Going back to the slides, selection sort has the advantage of being easy to code. All it involves is one loop nested within another loop, and then a swapping section of code. But other sorting algorithms are not so easy to code. and we'll find that out when we get to namely shell sort and quick sort. So the next sorting algorithm that we're going to talk about is insertion sort. Insertion sort is a sorting algorithm that treats the input, which is once again an unsorted array of elements, as two parts, a sorted part and an unsorted part, and repeatedly inserts the next value from the unsorted part into the correct location in the sorted part. So this sounds extremely similar to selection sort, and indeed they are closely related. The difference is, in selection sort, we went searching through the unsorted portion of the array, finding the smallest element, and then that element got put into the sorted portion of the array. Insertion sort, on the other hand, what it's going to do is just take the very next item in the unsorted portion of the array and put it into the sorted portion of the array. Now, of course, initially putting it into the end of the sorted portion of the array, it won't be in sorted order, and so what it does is it then finds, by swapping elements, where it belongs in the sorted portion of the array. So to better understand how this works, we'll go ahead and look at an example. Once again, we will refer to zybooks. So to start, you will notice that there are two loops. So once again, similar to selection sort, there's a for loop and then a nested while loop. And now what's interesting is inside of this nested while loop, we have some swapping code. And so we'll see in a second here kind of what that swapping code is doing. We'll go ahead and read the comment here. Insertion sort treats the input as two parts, a sorted and unsorted part. Variable I is the index of the first unsorted element. Initially, the element at index 0 is assumed to be sorted, so it starts at 1. Yeah, so that's interesting, right? If we look at the for loop, I begins at 1 instead of 0. And then j begins at I. And so they completely ignore the very first element in the array. And the reason being is they're assuming that this is now a sorted portion of the array. And of course it's sorted. There's only one element in this subarray here, and so compared to itself, it's therefore sorted. And so what's going to happen here is they're going to add the 6 into the sorted portion of the array. Now initially, 6 is going to be to the right of the 32, which is not sorted order. So what they do is they are going to swap, and that's where this swapping section of code will come in handy. They're going to swap the 6 with the 32, thus sorting the sorted portion or partition of the array. So let's go ahead and take a look. Variable j keeps track of the index of the current element being inserted into the sorted part. If the current element is less than the element to the left, the values are swapped. So 6 was added to the sorted portion. The element to its left was 32. 6 is less than 32, therefore they swapped. Now 6 has reached the very beginning of the sorted portion of the array, and so this check is done. But you'll find soon now that sometimes multiple swaps are needed to get the newly added element into the position that it belongs. So read the bottom here. Once the current element is inserted in the correct location in the sorted part, I is incremented to the next element in the unsorted part. And so I got incremented to index 2, which had a value of 15. So 15 was added to the sorted portion of the array. And what they did here was 15 is less than the element on its left, which is 32. Therefore, they swapped the 15 and the 32. And then what they did was they made another check. They checked to see if 15 was less than 6, which is not the case. which means 15 is indeed in the correct location that it belongs within the sorted portion of the array. But if, for example, 15 had been, let's say, a smaller number, then it would have swapped with the 6. And we'll actually see that with the next element here. So we continue on, and the next item or element to be added into the sorted portion is the 3. And the 3 is less than all of these values in the sorted portion. So it's going to swap with every single one until it reaches the very beginning of the sorted list, or sorted array. And so if we read the comment below, if the current element being inserted is smaller than all elements in the sorted part, that element will be repeatedly swapped with each sorted element until index 0 is reached. So there we have it, 3 reaches index 0, and now the sorted portion of the array is in sorted order. And the very last element to be added is the 20. And so I increments to index 4, which is the 20. 20 will get added in to the sorted list. It is less than the 32, therefore 20 and the 32 will swap. And then a check will be made to see if 20 is less than the 15, which is not the case, and so the swapping stops. And there you are. Once all the elements in the unsorted part are inserted into the sorted part, the list is now sorted. So we're going to go back to the slides here. One benefit that insertion sort presents is it actually turns out it's more efficient with nearly sorted lists. And I understand that does sound strange because you would think, well, wouldn't all sorting algorithms be efficient with a list that's already nearly sorted? The answer is no. Some sorting algorithms will perform at the exact same efficiency regardless of if the list is already sorted or not. Insertion sort is not one of these. It actually performs better if the list is already indeed sorted. And why am I mentioning this? Well, the next sorting algorithm in shell sort uses the insertion sort algorithm. And this is actually common among some of the sorting algorithms, is using a different sorting algorithm under its most efficient case, which in the case of this insertion sort is a nearly sorted list. So the next sorting algorithm is shell sort. Shell sort is a sorting algorithm that treats the input as a collection of interleaved lists and sorts each list individually with a variant of the insertion sort algorithm. Shell sort uses something called gap values to determine the number of interleaved lists. A gap value is a positive integer representing the distance between elements in an interleaved list. And for each interleaved list, if an element is at index I, the next element is at index I plus gap value. So I understand this can be somewhat complicated to understand just by reading the words, so we will look at an example shortly applying these definitions. First, let's go ahead and look at the actual shell sort algorithm. So step 1, shell sort begins by choosing a gap value, in this case k. K is just a variable representing some sort of number. And then what it will do is it's going to sort k number of interleaved lists in place. Shell sort then finishes by performing a standard insertion sort over the entire array. because the interleaved parts have already been sorted, the smaller elements will be close to the array's beginning and the larger elements towards the end. And then insertion sort can then quickly sort the nearly sorted array. And so the idea is sort the interleaved lists first, creating a nearly sorted array, and then apply insertion sort over the entire array. And because it's already nearly sorted now, it'll be very efficient. So any positive integer gap value can be chosen. In the case that the array size is not evenly divisible by the gap value, some interleaved lists will have fewer items than others. That's not a huge issue. So we'll go ahead and take a look at shell sort. Once again, we will refer to Zybooks for this. And so, just to start off with what a gap value means, if a gap value of 3 is chosen, shell sort views the list as 3 interleaved lists. Starting at index 0, we have 56, 12, and 75. And so you can see all the orange colored elements are going to form a single interleaved list. And then 42, 77, and 91, that will form another interleaved list. And then 93, 82, and 36, and that will form the last interleaved list. So what is determining these placements? Well, it's the gap value. If you notice, starting at index 0, every third element will be a part of that interleaved list. So we have 56, 1, 2, 3. So 12, 1, 2, 3. So 75. And the 3 is because the gap value of 3 was chosen. So we start with 42, 1, 2, 3, 77, 1, 2, 3, 91. And so that's how the gap value is used to form these interleaved lists. So once you form them, now you can kind of think of them as completely separate arrays. And so that's what they've done here. And what they do is you apply insertion sort on all of these interleaved lists. And so since they're small, it's going to be very fast. And so you can see here now each of these interleaved lists is sorted. And if we look at it in terms of the actual array, this is what it would look like. And what you can see is the result is not a sorted list, but is closer to sorted than the original one. In other words, the 3 smallest elements are towards the beginning of the list and the 3 largest elements are towards the end of the list, meaning the entire list is already nearly sorted. And this is what we want in order to apply the final insertion sort that is more efficient given a nearly sorted list. So here what they're doing is they're comparing a normal insertion sort against the original array, and they're counting the number of swaps it takes, which is a very common thing in terms of sorting algorithms, is comparing the number of swaps. And so what you can see here is they're applying the insertion sort algorithm until eventually the entire array is sorted, and it took 17 swaps. So now what they're going to do on the array to the right here is apply the shell sort algorithm. But in this case, they'll have already included the sorting of the interleaved lists, which took, I believe, 4 swaps. Yeah, so the sorting of the interleaved list required 4 swaps, and then running this final insertion sort, if we look at this, 1 swap, a second swap, and then a third swap. And so those 3 swaps plus the 4 required to sort the interleaved list has a total of 7 swaps. Far more efficient than just running a normal insertion sort over the entire array. So if we scroll down here, we can actually look at some of the code It's fairly complex, but you can see here, this is the insertion sort that's slightly modified for interleaved lists. It's going to look very similar to the original insertion sort algorithm. And then if you look further down, you can see right here, in this case, they provide multiple gap values. And so the idea is initially they have you sort the list with a gap value of 5. And then what they do is they have you sort it again afterwards. So the resulting list from the gap value 5 will get sorted using a gap value of 3. Neither of those having yet applied the full insertion sort over the entire array. And that's actually what the gap value of 1 is for, is that actually is insertion sort over the entire array. And so yeah, basically the whole thing is just continuously applying a gap value to create those interleaved lists and apply insertion sort on those interleaved lists. So that's shell sort. So you can see it's getting more and more complex, right? But shell sort is extremely efficient, and so that's kind of the trade-off. So the next sorting algorithm is quicksort. Quicksort is a sorting algorithm that repeatedly partitions the input, which is once again an array of unsorted elements, into a low and high part. And each of those parts is unsorted. Then what it's going to do is recursively, so here's where a use of recursion comes in. It then recursively sorts each of those parts. And so the low and high parts are going to get determined by something called a pivot value. So yeah, to partition the input, quicksort chooses a pivot value to divide data into low and high parts. So essentially, the pivot value, what's going to happen is a pivot value will be chosen, and then you're going to sort or traverse through the entire array, checking each element against the pivot value. If an element's value is less than the pivot value, then it will go into the low partition. If an element's value is greater than the pivot value, then it will go into the high partition. The pivot value can be any value within the array being sorted, but commonly the value is whatever is in the middle of the array. So this is somewhat similar in terms of concept as the binary search, choosing a middle value and then doing some comparisons based on the value of that middle value. But it is slightly different. So some of the steps to quicksort: to partition the input, the quicksort algorithm divides the array into two parts, referred to as the low partition and the high partition. All values in the low partition are less than or equal to the pivot value. All values in the high partition are greater than or equal to the pivot value. And the values in each partition are not necessarily sorted. So you're just placing them in the partition each time. Once partitioned, each partition needs to be sorted. Quicksort is typically implemented as a recursive algorithm using calls to quicksort to sort the low and high partitions. The recursive process continues until a partition has 1 or 0 elements, and thus is already sorted. And so what I mean by each partition needs to be sorted, and quicksort is typically implemented as a recursive algorithm, really what this is saying is each partition is going to get partitioned again, and then those partitions will get partitioned again, and those partitions will get partitioned again, until eventually each partition only contains a single element. And then what you'll find is once you all partitions have reached a point of being a single element, that you have now reached sorted order. Let's go ahead and take a look at this using, once again, Zybooks. So this first part we're going to look at is just the partitioning process. It's not the entirety of the quicksort algorithm. So somewhat ignoring the code down here, let's just abstractly look at what's going on. They're choosing the midpoint to be the pivot point. And so the pivot's value is 6. So essentially what we're going to do is we're going to create a high partition which will have cell blocks of color yellow or gold, and then a low partition which has cell blocks being colored gray. And we're going to use the pivot value of 6 to do this. So we start at index I, or L here, and essentially what's going to happen is we're just going to check every single element in the array and determine whether or not it belongs to the low or high partition. But it isn't going to do this in a linear fashion. It's going to start on the left and determine if this left element here, the 7, is less than the 6 or greater than the 6. In this case, 7 is greater than the 6, and so it does not belong in the low partition. And so what the algorithm will do, this partitioning algorithm, is it's going to keep track of this 7 and move over to the other side of the array where the high partition should be, and now check the elements in the high partition for a fault in anything that should not belong in the high partition. So in this case, they check the 8. The 8 is indeed greater than the 6, so it does belong in the high partition. They check the 18. The 18 is indeed greater than the 6, so it belongs in the high partition. Now they check the 6, and the 6 is not greater than 6, and so they're saying that the 6 does not belong in the high partition. Therefore, what they're going to do is swap the 6 and the 7. And so you can see that's what they're doing here. They swap the 6 and the 7. Now the 6 still remains as the pivot value. That hasn't changed. Just because its value has swapped or its location has been swapped doesn't mean the pivot value changes. And so what you can see is there's still one element left in here, the 4, and so the 4 needs to be checked. And so you can see 6 is now part of the low partition. 7 has been added to the high partition. 4 is less than 6, therefore it belongs in the low partition. And now what they're doing is a part of the algorithm that determines that you should stop, that both the low partition and high partition have indeed been formed. Yep, and then once partitioned, the algorithm returns H, indicating the highest index of the low partition, and the partitions are not yet sorted. So yeah, you'll notice that both the high partition and the low partition are not sorted. 6 is greater than 4, so 4 should actually be swapped with the 6. And the 8 is less than the 18 here, so they should be swapped. But the thing is, that's not part of this partition's job. This partition, its job is to just create a low partition and a high partition in no particular order. And so that's what it's done. And so that's the partitioning algorithm. But now we go down to quicksort. If we look at the quicksort code real quick here, you'll notice it actually calls the partitioning algorithm and then it recursively calls itself. And so we'll look at kind of what it's doing here. It calls that partitioning algorithm, choosing 6 to be the pivot, which then partitions accordingly. So we've already seen how this works. And now those recursive calls to itself what it's doing is it's going to repartition each partition that was just formed. So the low partition is going to get repartitioned, and the high partition will get repartitioned. And so you'll see that the low partition, what's going to happen here is the 4 will become the new low partition, and the 6 will become the new high partition, using that same partitioning algorithm. And then it will call quicksort again, once again choosing the low and high partitions. But what you'll notice is that each partition now only contains a single element. And this is what's going to be the base case of the stopping condition for the recursive algorithm. And so you can see right here, base case is 0 or 1 elements, partition is already sorted. And so they're already now sorted. And so the next job is going to move back up to the original high partition and repeat the process. So the quicksort algorithm will be recursively called. It's going to partition based on the 18 here. And so the 7 and 8 will form the low partition, and the 18 will form the high partition. And then once again, we call quicksort on the low partition, and then we call quicksort on the high partition. The low partition only has 2 elements, so it's going to form a low partition with 7 being in the low partition, and then 8 in the high partition. Call quicksort on those 2 respective partitions, and each of those respective partitions only contains 1 element, and there's the base case or the stopping condition for this branch of the recursion. Now, we'll go back to the 18, which is in the high partition, and it also only contains a single element in its partition, which therefore is, once again, you've reached the stopping condition, and so it's already sorted. And so now we're done. As it turns out, if you notice, all the elements are now sorted. The 4, the 6, 7, 8, and 18 it's now sorted in ascending order. So as it turns out, this partitioning process, continuously partitioning, sorts the elements. And this is what I was talking about in terms of quicksort is one of the fastest algorithms out there in terms of sorting. But the trade-off is it's confusing and it's fairly hard to implement. So yeah, that's the quicksort algorithm. You won't need to worry so much about the code of these algorithms. So quicksort, shell sort, you don't need to worry about the code for them. You mainly need to worry about abstractly what's going on, how they work, right? But you don't need to worry about the code. And so the final sorting algorithm that I'm going to cover is merge sort. Merge sort is a sorting algorithm that divides a list into 2 halves, recursively sorts each half, and then merges the sorted halves to produce a sorted list. And so this sounds somewhat similar to quicksort, and it is, but there are certainly some differences. So the recursive partitioning continues until a list of 1 elements is reached. So once again, similar to quicksort. The merge sort merges the 2 sorted partitions into a single list by repeatedly selecting the smallest element from either the left or the right partition and adding that element to a temporary merged list. Once fully merged, the elements in the temporary merged list are copied back to the original list. And so herein lies a big difference between merge sort and quicksort. Quicksort, right, we were using this pivot value to form a low and high partition. Merge sort doesn't do that, it just splits it down the middle. And since it does that, the partitioning process does not automatically sort the elements like quicksort does. And in order to add that sorting portion, that's where the merging of two sorted partitions comes in play, repeatedly selecting the smallest element from either partition into a temporary partition or list, and then that temporary list gets copied over into the original list. So we'll go ahead and look at an example of this on Zybooks. We won't cover the radix sort. Okay, present. Okay, so here's our array of unsorted items or elements. And what they do here is they find the middle of the array and split it accordingly. You'll notice it's not sorted, it's not a low partition or a high partition, it just simply is split down the middle. And then we do it again. With each of those separate partitions, we split them again. And then with those partitions, we split them again, and so on and so forth until every single partition only contains a single element. And so you can see they've done the same with the right side as well. And so you can see what's left is 3, 11, 8, 18, 4, and 25, all in single partitions. And now the next step is to merge them back together. And so in doing so, they're going to take the smallest element from each partition and add that into a temporary list. So, so here's the starting elements, and we'll start from the left and work our way to the right. 3 and 11. Well, 3 is less than 11, so it goes first, and then 11 goes in. Now you have the 3 and 11 and the 8. 3 was less than 8, so it came first, and then the 8, which was a less than 11, came, and then it was 11. And so the process continues, right? Continuously selecting the smallest element items, the 3, and then the 4, the 8, the 11, the 18, and the 25. And so this is that merging part of merge sort. And as you can see, the result is now this final array here is sorted. 3, 4, 8, 11, 18, 25. So it's in ascending order. And so this is all the code for the merge sort algorithm. Once again, it's quite complex. I'm not going to expect you to know the code. This is something you'll learn more in data structures, but you should understand, generally speaking, how merge sort works. All right, and that's all I have for you for the sorting lecture.